This is the third lecture of the lecture series entitled Bracket Algebra. Let me first mention the essential points of the previous second lecture. We defined what is Hermitian conjugation operation. It is taking complex conjugation followed by transpose. While star represents complex conjugation, the symbol T represents transpose and the dagger symbol stands for Hermitian conjugation operation. Operators are represented by square matrices. So A hat is A, B, C, D, a 2 cross 2 matrix, or a 3 cross 3 matrix A, B, C, D, E, F, G, H, I. The Hermitian conjugation of A hat is A hat dagger, which is A star, C star, B star, D star. In case of 2 by 2 matrix, A star, D star, G star, B star, E star, H star, C star, F star, I star. In case of 3 by 3 matrix, we emphasized that ket dagger is bra and ket psi dagger is bra psi. Also bra dagger is ket and so bra psi dagger is ket psi. Clearly bra psi and ket psi are related through Hermitian conjugation. If ket psi is a column matrix A, B, C, then bra psi is a row matrix A star, B star, C star. If bra psi is a row matrix A, B, C, then ket psi is a column matrix A star, B star, C star. If ket psi is C ket phi, then bra psi is C star bra phi. And if bra psi is C into bra phi, then ket psi is C star ket phi. Let us address a very pertinent question in this lecture, namely, why do we require two notations? That is, why did Dirac introduce two notations, namely bra and ket? Was it really necessary? Let us consider a 2D vector space defined by basis unit vectors x hat and y hat. So this is x-axis and x hat is the direction of increase of x coordinate. This is origin. And this is the y-axis perpendicular to x hat, and y hat is the direction of increase of the y coordinate. The basis unit vectors, with the help of which we have defined or described the 2D vector space, are special choices since they satisfy two properties. Number one, x hat dot x hat is unity, y hat dot y hat is unity. So x hat and y hat are vectors of unit magnitude. Number 2, x hat dot y hat is 0. Y hat dot x hat is 0. This is because x hat and y hat are perpendicular to each other. Let us now give a matrix representation to the unit vectors, and with the matrices try to generate the four numbers 1, 1, 0, 0. Let us represent x hat by a column matrix, say 1, 0, and y hat by another column matrix 0, 1. Now consider x hat dot x hat equal to 1. X hat is a column matrix 1, 0, so we have two column matrices and we cannot take their product. Consider y cap dot y cap equal to 1. Y hat is a column matrix 0, 1, so we have two column matrices and we cannot take their product. Consider x cap dot y cap equal to 0. X hat is a column matrix 1, 0, y hat is another column matrix 0, 1, so we have two column matrices and we cannot take their product. Consider y cap dot x cap equal to 0. Y hat is a column matrix 0, 1, x hat is another column matrix 1, 0, so we have two column matrices and we cannot take their product. Clearly we fail to generate the numbers 1, 1, 0, 0 if we carry on our business with column matrices only, that is, stick to column matrices only. we have to think of ways to generate the numbers 1, 1, 0, 0. The 2D vector space has been defined by x hat equal to column matrix 1, 0 and y hat equal to another column matrix 0, 1. As we cannot do business only with column matrices defined in 2D vector space, let us define row matrices by taking Hermitian conjugates. Corresponding to the column matrix x hat equal to 1, 0, let us define the row matrix 1, 0 dagger equal to 1, 0. Corresponding to column matrix y hat equal to 0, 1, let us define the row matrix 0, 1 dagger equal to 0, 1. Let us check the relations. Consider x hat dot x hat equal to 1. Consider the left hand side x hat dot x hat. Put row matrix 1, 0 for the first x hat and put column matrix 1, 0 for the second x hat. Product gives 1, so the number 1 is generated. Consider y hat dot y hat equal to 1. Consider the left hand side y hat dot y hat. Put row matrix 0, 1 for the first y hat and put column matrix 0, 1 for the second y hat. Product gives 1, so the number 1 is generated. Consider x hat dot y hat equal to 0. Consider the left hand side x hat dot y hat. Put row matrix 1, 0 for x hat and put column matrix 0, 1 for y hat. Product gives 0, so the number 0 is generated. Consider y hat dot x hat equal to 0. Consider the left hand side y hat dot x hat. Put row matrix 0, 1 for y hat and put column matrix 1, 0 for x hat. Product gives 0, so the number 0 is generated. It is thus clear that to switch over to matrix representation we need number 1 column matrices, number 2 row matrices. We can add 2 column matrices, and this means that the column matrices are defined in the same space, a 2D vector space. We can add 2 row matrices, and this means that the row matrices are defined in the same space, a 2D vector space. But we cannot add a row matrix to a column matrix. And this is because row matrices and column matrices are defined in different spaces, different 2D vector spaces. Also, since the row matrices have been generated from the column matrices, for instance row matrix 1, 0 from column matrix 1, 0 and row matrix 0, 1 from column matrix 0, 1, by taking Hermitian conjugate, it follows that column matrix space and row matrix space are dual or Hermitian conjugate of one another. We thus have come to the end of our discussion. To describe the 2D vector space, we thus need column matrices defined in that 2D vector space, and also we need row matrices defined in a dual 2D vector space. We thus require 2 notations. One for column matrices, let us call it ket, defined in ket space, which is the 2D vector space, and another for row matrices, let us call it bra, defined in a space that is dual to ket space. Let us call it bra space. We rewrite the relations in our new notation and check how the numbers 1, 1, 0, 0 are generated. X cap in column matrix representation is 1, 0, which is denoted by, say, ket 1. X cap in row matrix representation is 1, 0 dagger, which is 1, 0 and is denoted by bra 1. Y cap in column matrix representation is 0, 1, which is denoted by, say, ket 2. Y cap in row matrix representation is 0, 1 dagger, which is 0, 1 and is denoted by bra 2. First relation is x hat dot x hat equal to 1. Left hand side is x hat dot x hat. Replace first x hat by bra1, which is row matrix 1 0, and second x hat by ket1, which is column matrix 1 0. So x hat dot x hat gives bra1 ket1, which generates the number 1. Second relation is y hat dot y hat equal to 1. Left hand side is y hat dot y hat. Replace first y hat by bra2, which is row matrix 0 1, and second y hat by ket2, which is column matrix 0 1. So y hat dot y hat gives bra2 ket2, which generates the number 1. Third relation is x hat dot y hat equal to 0. Left hand side is x hat dot y hat. Replace x hat by bra1, which is row matrix 1 0, and y hat by ket2, which is column matrix 0 1. So x hat dot y hat gives bra1 ket2, which generates the number 0. Fourth relation is y hat dot x hat equal to 0. Left hand side is y hat dot x hat. Replace y hat by bra2, which is row matrix 0 1, and x hat by ket1, which is column matrix 1 0. So y hat dot x hat gives bra2 ket1, which generates the number 0. With a switch of notation from x hat to ket1 equal to 1 0 column matrix, and y hat to ket2 0 1 column matrix, we have defined and described 2D vector space. While ket1 and ket2 are in ket space, the corresponding bra1 and bra2 reside in bra space, that is dual to the ket space. Let us end up asking the question, can we multiply a bra with a ket? We shall discuss this in the next class.